Hello and welcome to the tutorial. Today we'll create a complete 3D engine in Python, using only the Pygame and NumPy libraries. Later, you can use this engine to create your own 3D games, such as a 3D platformer. However, in this tutorial, I'll only show you the basics of 3D engines. You only need 4 files: main.py, camera.py, transform.py and mesh.py. Alright everyone, let's start really simple. We import the Pygame library. First we set the window size, width equals 800, and height equals 600. Next we create the window and store it in a variable called screen. This screen is our drawing surface. Now we build the game loop skeleton. We create a running flag and start a loop that runs while the program is active. Inside that loop we check events. If the user clicks the window close button, we stop running and exit the loop. We set up a clock and cap the frame rate. We call the clock tick function each frame to limit it to 60 frames per second. We clear the screen each frame by filling it with a background color, here a dark gray. After drawing everything for the frame, we update the display so the new frame becomes visible. We're now inside the file mesh.py. This file will handle all the data that defines a 3D object. In a 3D engine, every model is made up of something called a mesh. A mesh is simply a collection of points in space, called vertices, and lines that connect them, called edges. Together, they form the wireframe of any 3D shape, like a cube, a pyramid, or even a complex model imported later on. Here, we're creating a class named mesh. Inside the constructor, we'll just store 2 things, the vertices and the edges. The vertices represent the coordinates of each point in 3D space, and the edges describe how those points are linked together. Right now, this class doesn't do much more than store data. But later, it will become a key part of our rendering system, once we add transformations, rotations, and real 3D projections. So this simple structure will serve as the backbone for every 3D object in our engine. Now click on transform.py. This file is responsible for all kinds of transformations in 3D space, things like moving, scaling, or rotating objects. For now, we'll only focus on rotation around the y-axis. That's the vertical axis, meaning the object will spin left and right. We import NumPy because it helps us handle all the math easily. Then we define a function called rotate_y, which takes 2 arguments, vertices and angle. The vertices represent all the 3D points of the object, and angle comes from main.py. It controls how much we rotate the object. Inside the function, we create a rotation matrix using cosine and sine. When we multiply the vertices by this matrix, the points are rotated smoothly around the y-axis. We'll call this function from main.py every frame, and update the angle there, so the rotation becomes continuous and animated. Perfect. We can go back to main.py and use it. Alright, so now we're inside the main file. At the top, we first import our new classes, Mesh and Transform. The window is already set up from before, so now we can go ahead and create our first cube. To do that, we first define a list of vertices. These are all the corner points of the cube. Then we create a list of edges that connect those vertices together. After that, we create a mesh instance and pass in our vertices and edges. And now comes an important fix. We need to swap screen.fill and pygame.display.flip. That's because if we clear the screen after flipping, the cube will flicker every frame. So we always fill the screen before updating the display. Inside the game loop, we clear the screen first, then rotate our cube around the y-axis by a small angle. This rotation is handled by our transform function. Next, we draw all the cube's edges using pygame.draw.line, connecting each pair of points. When you run this, you should see a white cube rotating smoothly in the center of your screen. Now that our cube already rotates around the y-axis, let's make it rotate around the other axes as well. To do that, open the file called transform.py. We already have the function called rotate_y. Now let's add two more functions, one for rotating around the x-axis, and one for rotating around the z-axis. Both of them work almost the same way. They use a rotation matrix, but with slightly different positions of sine and cosine. For example, the x rotation only changes the y and z values, while the z rotation only affects x and y. We can simply copy the code and only have to change a few things. Now open the file, main.py, again. We already have the cube rotating around the y-axis. Now let's make it rotate in all three directions, x, y, and z. To do that, first create three separate variables at the top of the file, right where we defined the angle before. Call them angle x, angle y, and angle z, and set all of them to 0. Then, in the game loop, instead of using only one rotation, we'll apply all three, one after another. So, after getting cube.vertices, call the functions rotate x, rotate y, and rotate z, in that order. After that, slowly increase all three angles so the cube keeps rotating smoothly. When you run the program now, the cube should rotate in all three directions, giving it a much more dynamic 3D look. In the next part, we'll start working on the camera system, so that we can move around the cube and look at it from different angles. And we can see it works, the cube rotates in all directions. Now click on the file, camera.py. This file will be responsible for how our 3D world is seen. Basically, it controls what the player's eyes would see. We'll create a class called camera. Inside the constructor, we define a position. By default it's a bit behind the cube, so we can actually see it. Then we add some parameters like the field of view, near plane, and far plane. Next, we'll write a method called project. This will take our 3D vertices and convert them into 2D screen positions, using a bit of math from perspective projection. The idea is simple. The farther a vertex is away from the camera, the smaller it appears on the screen. To prevent division by 0, we also check that z is never exactly 0. At the end, the method returns a list of projected 2D points that we can later use in our main file to draw the cube in real 3D perspective. Before, we divided the field of view by 2 right when converting it from degrees to radians. But that's actually not correct, because the projection formula already divides it by 2 later, inside the tangent function. Doing it twice makes the field of view look way too narrow. We can go back to our main file and actually use it. First, we import the camera at the top, right next to our other imports. Then we create a new camera instance, just like we did before with our cube. Now we're going to connect the camera to our cube. Instead of drawing the cube's raw, rotated vertices, we'll send them through the camera's project function. This function takes all the 3D points and converts them into 2D screen coordinates, based on the camera's position and field of view. The result is that our cube now has real depth and perspective. When we move or rotate the camera later, we'll actually see the cube from different angles, just like in a real 3D environment. And we see the cube is drawn in real 3D perspective. Go back to camera.py. Now let's extend our camera to make it move and look around. First, we add two new variables, yaw and pitch. Yaw controls the horizontal rotation, meaning turning left or right. Pitch controls the vertical rotation, looking up or down. Both start at 0, so the camera faces forward when the program starts. The move function is straightforward. It simply adds a direction vector to the camera's current position. That means we can move forward, backward, or sideways relative to where the camera is looking. Next, we add a function called getForwardVector. This returns the direction the camera is currently facing, based on its yaw and pitch. It uses simple trigonometry to calculate the x, y, and z components of that direction. Then, we add getRightVector. This gives us the direction to the right of the camera. It's used for strafing left and right with movement controls. After that, we add a rotate function. This updates the yaw and pitch values depending on input, for example, when we press the arrow keys. We also clamp the pitch between -90 and +90 degrees so the camera can't flip upside down. Finally, we expand the project function to include the camera rotation. We create two rotation matrices, one for yaw and one for pitch, and multiply them together into a single rotation matrix. This allows the camera to look around while keeping the projection mathematically correct. That's all that's new here. The camera can now move in 3D space and freely look around using yaw and pitch. In the next step, we'll go back to the main file and make it react to keyboard input, so we can move around the cube using WASD and rotate the view with the arrow keys. Let's go over what changed in our main file. First, right after the rotation angles, we add two new variables, move speed and rotation speed. These define how fast our camera moves and how quickly it turns. Inside the main loop, right after the event section, we create a new variable called keys that checks which keys are currently pressed. Then we add a new block for camera movement. Here we call our cameras getForwardVector and getRightVector functions. When pressing W or S, we move the camera forward and backward. When pressing A or D, we move it left and right. This movement happens relative to the camera's orientation, so pressing W always moves you in the direction you're currently facing. Now we try to run it, and we see that when we press W, the window closes, and we get an error. This is because we define the position as an integer, not a float. Everything should work now. Below that, we add the camera rotation part. Pressing the left or right arrow key rotates the camera horizontally using yaw. Pressing up or down rotates vertically using pitch. Those two blocks together are what make the camera interactive. Everything else in the code, the cube creation, the projection, and the drawing, stays exactly the same. The only other small change is that we keep the cube rotating slowly, so the 3D space is easier to understand when we move around. That's all that changed. Now the scene reacts to WASD and arrow keys, and you can freely fly around the cube in real 3D. If we run this, we'll see that we can rotate the camera. But it also has some bugs, so we'll try to fix them all in the next part. Alright, now we're going to fix all the weird camera bugs we had earlier. Let's start by improving how the camera's forward direction is calculated. Before, it only used yaw and ignored pitch. That's why movement felt strange when looking up or down. Now, I'm updating the formula to use both yaw and pitch, so the forward vector always points exactly where the camera is facing. Next, I'm fixing the right vector. It used to be a simple horizontal direction based on yaw only. Now, I'm creating it using the cross product between the forward vector and the world's up direction. This makes sure that moving left and right always stays consistent, even when you look up or down. Then I'm adding a limit to the pitch rotation, so you can't flip the camera upside down anymore. The pitch value is now clamped between -90 and +90 degrees. After that, we're improving the projection function. I'm adding a more stable rotation system that uses both the yaw and the pitch properly. This helps prevent those strange distortions that used to appear when you moved and looked around at the same time. Now we're going to add a more advanced version of our rotation logic. Instead of just rotating around a global x-axis, we'll make the camera rotate around its own local right-axis. To do that, we use something called the Rodriguez rotation formula. This formula builds a rotation matrix from 3 parts: the cosine of the rotation angle, the sine of the angle, and the normalized rotation axis, which in our case is the right direction of the camera. The idea is that every rotation in 3-dimensional space can be expressed as a combination of a base identity matrix, a scaled version of the axis vector, and a special cross-product term that handles the circular movement. With this matrix, we can rotate the camera around its own axis smoothly, even if we've already turned the camera horizontally. That means when we look up or down, it no longer tilts sideways or drifts. The motion stays completely stable and natural. Don't worry if this part looks complicated. This rotation matrix simply makes sure our camera rotates correctly around its own local axis. Without it, the camera would drift or tilt when we look up or down. But with this version, the rotation stays perfectly stable, no matter which direction we're facing. Now I'm changing this part to use the add symbol instead of NumPy dot. The add symbol in Python means matrix multiplication. It works exactly the same, but it's cleaner and easier to read. I'm adding near clipping. That means when the camera gets too close to the cube, the vertices in front of it won't break the projection or cause flickering anymore. Once all of this is done, the movement will feel smooth and stable, and the cube will render perfectly from every angle, even when you look all the way around it. Now I'm updating the part where we draw the cube edges. Before, we were directly accessing the vertex coordinates, which could cause errors if a vertex was too close or behind the camera. To fix this, I'm adding a check. If either the start or end vertex is none, we skip drawing that line. This makes sure that we only draw valid edges that are actually visible, and prevents any weird lines or crashes when the camera moves around. If we run this now, we will see that there are no more bugs. And that's it. Our 3D engine is now complete. We've got movement, rotation, a working camera, and full perspective projection. In the next part, we're going to take this even further. We'll start filling our cube, adding lighting and shadows, and even make it possible to load real 3D objects from the internet into this engine and view them in real time. And here's the deal. If this video gets more than 500 views, I'll make a full part where we use this exact engine to build an actual 3D platformer game in Python. So stay tuned, because that's where things are going to get really interesting.